Hi, I'm Ed Ayres. I'll be presenting results from a project that my colleagues and I recently finished, validating SMAP soil moisture at forested and unforested NEON sites. This was a really collaborative project, and I've listed all of the co-authors here, as well as others who contributed to the project. So soil moisture is, of course, really important for forest health. So there's this need for regional to global scale soil moisture data from forests. But SMAP, with SMAP being one of the major soil moisture data providers, the SMAP soil moisture data for forests is all flagged as potentially unreliable due to interference from the water content of the plant canopy interfering with the satellite's measurements. In addition to that, forests have also been very underrepresented in previous SMAP validation campaigns. In the most recent campaign, they only accounted for about 1% of sites, despite the fact that forests occupy about 20 to 30% of the land surface. So we really don't know how well SMAP is performing in forests. This is the data that we used for this. For SMAP, it was 0 to 5 centimeters soil moisture with a temporal resolution of 2 to 3 days, a spatial resolution of about 1,000 square kilometers, and close to global coverage. For NEON, we used the shallowest sensors that's about 6 centimeters deep, the 30-minute averaging interval with a spatial resolution of around 0.1 square kilometers, and that's because it comes from 5 soil plots spaced up to about 50 meters apart. And this is generated from 47 sites dotted around the US, representing a really wide range of ecosystems and soil types. And on the lower left picture here, you can see in the white areas, the areas that are typically flagged by SMAP. And you can see that those white areas really closely match forest distributions globally. So just emphasizing how much of the forested soil moisture data is flagged by SMAP. I won't spend much time on this slide, but I did want to mention, given the huge differences in the NEON versus SMAP spatial scales, we wanted to check that the environments that they were measuring were broadly similar. And the upshot of this was that despite these huge differences in scale, the NEON and SMAP measurements did seem to reflect similar environments. So making these comparisons did seem to be fair. Once we combined the data, we had over 12,000 measurements from 40 different sites, 21 unforested sites, 19 forested sites, and collectively this represented 88 site years of data. On the right here, I've shown the data for one of our sites with the NEON data in red, the SMAP data in black. And once we produced these correlations, we calculated 6 different correlation parameters: the root mean squared deviation, the unbiased root mean squared deviation, which I've highlighted because that's the primary metric that SMAP uses to quantify performance. And that you can think of that as representing the sensitivity of SMAP to changes in soil moisture. The mean difference, which includes measurement bias as well as representativeness errors, the absolute mean difference, the Pearson correlation statistic, and the slope of the correlation. So first, looking at the unforested sites, we found that SMAP was sensitive to changes in soil moisture. The unbiased root mean squared deviation was 0.05 meters cubed per meters cubed. So no real surprise here. There have been a ton of previous validation studies of SMAP at unforested sites. But what was encouraging to see was that the results from the NEON validation were very similar to previous sparse networks validations. So that gives us some confidence that NEON is performing at least as reliably as those other sparse networks, and gives us some confidence when we move on to looking at the forested sites where there haven't been very many previous validations at all. So looking at those forested sites, we found that the correlations were consistently weaker, but that the SMAP data still contained useful information. So the unbiased root mean squared deviation was around 0.06 meters cubed per meters cubed. So indicating that you can identify temporal trends in soil moisture in forests, at least when you're aggregating across sites. In contrast, the absolute values were really not very reliable. The root mean squared deviation was 0.15 meters cubed per meters cubed. Some of that is due to representativeness errors, so certainly adding some more widely distributed sensors to the validation sites could help, but also a large proportion of it likely comes from SMAP measurement biases as well. And on the bottom here, I've just plotted histograms of some of these correlation parameters for the forested sites in orange and the non-forested sites in blue. And again, you can see that these correlations in forests were generally weaker, but not terrible. So since we know that SMAP is sensitive to vegetation water content, we looked for other NEON data products that we would expect to closely relate to that, and we identified 3 different data products: above ground biomass, NDII, which is a remotely sensed index of vegetation water content, and canopy height. And if we first look at these in relation to unbiased root mean squared deviation, which is the top row in this figure, you can see that all 3 showed a positive correlation with the unbiased root mean squared deviation. So that's kind of indicating that no matter how good SMAP gets at minimizing measurement biases, we're never going to see the same sensitivity to changes in soil moisture in forests that we do in unforested sites. But it doesn't increase to such a high value that it becomes kind of useless. So even at the high end for these densest, wettest canopies and tallest canopies, we're still seeing unbiased root mean squared deviations of 0.07 meters cubed per meters cubed. So perhaps not as sensitive as we would like, but not terrible either. Even more encouraging when we looked at relationships with mean difference, which is, as I mentioned, includes SMAP measurement bias and also root mean squared deviation. We found that 2 of these ecosystem properties were correlated with this. So you can see that was for NDII and canopy height. And that's kind of indicating that these SMAP algorithms may not be parameterized optimally for forests, perhaps also not surprising since SMAP was primarily focused on unforested sites. But it also indicates that these algorithms could be reparameterized to improve the performance by taking into account these ecosystem properties. Another thing we did was look at the sites with particularly poor correlations, which we defined as having an R of less than 0.3. There were 5 sites in this category, all of which were forested sites. And when we looked into what was going on here, we found that there were 2 causes. So for 3 of the sites, we saw clear signals of the SMAP data just saturating at very high water contents. And you can see this on the lower left time series, where the NEON data in red and the SMAP data in black. And you can see that the SMAP data is just flatlining at these very high soil moistures for almost the entire growing season. So again, that's kind of indicating that the SMAP algorithms are not well parameterized for these sites and perhaps forested sites generally. The other issue that we saw, which we saw at 2 sites, was particularly large variation in soil moisture among the different NEON soil plots. And so that either could indicate data quality issues, perhaps one of the sensors wasn't working properly or had a poor installation, or perhaps just there's particularly high spatial variability at those sites. But again, there's something that we could do to improve that. So of course, ensuring that our in situ measurements are as accurate as possible, trying to replace malfunctioning sensors in a timely manner, or redoing installations if necessary, or possibly even removing locations if we consider them not representative of a spatial scale of interest, although I kind of hesitate to do the latter one there. So in conclusion, SMAP can reliably detect changes in forest soil moisture, at least when aggregating across widely distributed sites. If you're looking at an individual SMAP footprint, you definitely want to take a little more caution when you look at those trends, because in some cases those correlations were quite good, and in other cases they were quite bad. In contrast, the absolute SMAP soil moistures are often not representative for forests, but there is some indication that reparameterizing the SMAP algorithms for forests could help by accounting for canopy height and vegetation water content. And encouragingly, there are already remotely sensed data that exist for both of these ecosystem properties globally. And as with any validation study, representativeness errors remain. So certainly adding some more widely distributed soil moisture monitoring locations to the forested validation sites would help, as would adding more forested core and sparse validation sites generally, especially for particularly underrepresented forest types like tropical forests. And I put at the bottom here the link to our preprint that describes all of these results and is currently under review. Thank you.